Good evening. My name is Rishikesh Bhor, and today me and my team are going to be presenting our project on stress profile analysis in open forging. My team members include Arpit Dwivedi, Arpit Upadhyay, Adil Gupta, Tanvi Joshi, and myself. Our objectives behind doing this project was to simulate open forging of an aluminum alloy NL beam which has a hexagonal cross section. We were going to forge it into uh, a workpiece having a circular cross section using titanium dies. Our second objective was to find out the stress profile at three distinct cross sections of the workpiece, one at the center, one at the end of the die, and one at the free end at the perpendicular longitudinal cross sections of the workpiece. Our third objective was to find out the deformation profile at the three cross sections mentioned above. I'll be handing over the presentation to Arpit Dwivedi to continue.
Yeah, thank you, Rishikesh. So now I would be talking about the motivation behind taking this project. So we all know that the forging is the most commonly used manufacturing process in all industries. So it is very intuitive to work on this forging and to see how things go on. So basically, we have taken the geometry and analyzed the situation, which further team members will tell you all about. So here we have taken about the case of cold working, where the tremendous forces are required. As you all know that the friction coefficient is different for the cold working and hot working. So application of such large forces means a large input of power from the industrial point of view. So we need to optimize that power and force. So basically obtain a good profit in the aspect of industries. So we also wanted to implement whatever content had been taught to us in our course ME206 Manufacturing Processes Part 1 in our college, in our practical life. So first of all, the forging. What is forging? Forging is basic a metal manufacturing process in which a workpiece is compressed between two dies. So the force is being applied from the dies, and the workpiece between them deforms under plastic situation and take the shape of the die which is being implemented on them. So the basic analysis is as done in the Ghosh and Malik book, where the workpiece is being compressed from the dies, and we have considered the two regions, the sliding and the sticking region in the geometry, and analyze the situation by taking an element from the one point end and one free end, and then applying the condition of von Mises stress criteria to obtain the variation of stress generated in the workpiece. This is about the simple geometry, but here we have taken an hexagonal geometry that would be further done using the numerical methods. It is very complicated to do it by hand and obtain an analytical solution. Forging can be of different types like open and closed. For our project, we have analyzed the situation of open forging. One important point is that the forging is having an edge over the casting because the strength of the forged material is greater than the cast material. As shown in this figure, the directional strength is provided because of the grain directions. In casting, the grain are oriented in very random directions, which make it anisotropic and hence the strength is reduced. While in case of forged, where the grains are oriented in a particular direction, provide strength along a particular direction. So we have used the software ANSYS for solving our problem, and we all know that it is a very general purpose finite element modeling package which is used for obtaining a numerical solutions of different mechanical problems. We generally divide the material into various small grids, that is also known as mesh, and then obtain the values at particular nodes to obtain the results and all and compare it. We try to optimize the grain and grain sizing in different regions to obtain better results at better accuracy. Now I would like to invite Adil Gupta to further talk about this CAD model and further.
Okay, so CAD model that we used in this model is first of all the workpiece is made up of aluminum alloy and the dies are made up of titanium alloy. So the workpiece length is 40 centimeter and the edge length is 6 centimeter and it is a regular hexagon cross section. While the die is a circular cross section of radius 6 centimeter. The, we choose dimensions such that the areas are nearly equal. So when the material is compressed, it will not go out of the dies. And the reason why we use a plate is because we want to provide two types of boundary conditions into our model. So a fixed plate will provide different boundary condition than the free end. And here are the Young's modulus and density of the aluminum and titanium. Moving on to the boundary conditions. First of all the friction contacts have coefficient of friction 0.15 because we are doing cold forging. And as I have already said, the plate is fixed to the ground. So when the workpiece is compressed, it will it will provide force opposing force so that the workpiece will have more compressive stress there, as we will see in solutions also. Second, the displacement load is provided at the die joint. So the dies are moving laterally 1 centimeter towards each other, compressing the workpiece. As you can see in the graph, uh, the first 3 seconds the workpiece is being compressed, and the next 4 seconds the die are moving away from each other, relaxing the workpiece. Now I would like to invite Arpit Upadhyay to talk about the results of the model.
Thank you, Adil. So, what we see here, as Arpit told, ANSYS converts a body into mesh like of structure. So, we can see there's a net kind of thing over the whole hexagonal workpiece. That is what mesh is. Like, this is the mesh structure which ANSYS uses to solve the differential equations and apply the boundary conditions to. Now here we see various different cross sections, various different axial cross sections and lateral cross sections also. So this is the stress profile developed. Now aluminium's yield stress is somewhere around 2.3 into 10 raised to power 8, 10 raised to power 8 pascals. So now here if we see this graph, there's a slide in the side there's a color coded list. So basically, green color represents 2.35 into 10 raised to 8 pascals, and any color above green, it represents stress higher than that. So basically, any color above green represents that plastic deformation has already occurred there. So we see there's a maximum stress of 5.2, 5.2 into 10 raised to 8 pascals, which is quite high, and we are for sure that their plastic deformation has started. Now, the same thing we can analyze for various cross sections. In lateral, we see stress is very minimal, uh, especially the areas where dies are not there in lateral cross sections. But in axial ones, we can clearly see all of the edge and the boundaries. They are clearly in plastic deformation only. Now, if we move to the next slide, we can see the deformation profile. So we can clearly see the deformation maximized at the corners because we know corners are forced into the circular cross section. So they have to go under most amount of strain. So that is obviously evident by this deformation profile. And same goes for lateral cross sections also. The strain is minimum where dies are absent, and it is the maximum of strain it occurs at boundary condition only. The inner core it remains as it is. It is not under much strain. The strain is only for the outer layers. So this is the deformation profile of our workpiece. Now, if we go to the next slide, we can see the FEM simulation happening. So this is the FEM simulation for equivalent stress. So this is how actually stress is developed in the workpiece as dies close upon it. So yeah. So we see as the dies close upon each other, the stress starts developing, and this is the total deformation. Yeah, so deformation we can clearly see it is maximum at the corners, which was expected it to be. And if we see stress also, as the die is being compressed, as the die is close upon the workpiece, actually we have applied a boundary condition on the dies that the dies will come and touch each other. So that is called a displacement load. So we have applied a displacement load. So both those dies they come upon and touch each other and they move back. So as they do so, this is the following deformation profile and stress profile which we saw. It was developed. Now, for the next slide, I will like to hand over to Tanvi Joshi for explaining your result and conclusions.
Thank you, Arpit. I would take over for results and conclusions. So, in figure 5, which is on the left side of the current slide, we have plotted the force with respect to time. The pink line represents the total force. The red line, which is nearly coincident but slightly lower than the pink line, represents the force among the the x-axis along which the dies are being applied. The green and blue lines respectively show the forces along y and z axis. So we can see that the forces reach a peak at around 4 seconds, during which the dies are nearly touching. After that, since the dies are returning back to their original positions, the forces decline in magnitude. The figure on the right, figure 3, shows the maximum strains applied as well as the minimum strains applied at in a particular point along all of the cross sections considered. So the green line, which represents the maximum stress, we can see that it gains a peak at around 3 to 4 seconds of time, since during that time the dyes are really in close contact. After that, since the dyes go back, there's a sudden drop in the strain value, in the stress values. On to the next slide. The figure on the left shows a graph between the amount deformed versus with respect to time, and the maximum deformation is denoted by the green graph, whereas the minimum deformation is at some certain points is represented by the red graph. The table on the right again shows the exact values of results, and we can see that the minimum stress applied was around 1.7 megapascals, whereas the maximum stress was very high, which was around 528 megapascals, and clearly higher than the yield point of the aluminium alloy we've taken. Onto the next slide. So we have referred to Professor Pradeep Dixit's slides on ME202, a book on manufacturing sciences by Amitav Ghosh, and a few research papers and websites as shown in the slide. And we thank you all for listening to this presentation. And any questions shall be received very happily in the comment box. Thank you.